The crash involving Tiger Woods was not just a road accident. It became a real-world case study in physics, biomechanics, and the limits of human recovery. By analyzing the forces, the vehicle behavior, and the resulting injuries, we can better understand how extreme motion translates into real physical consequences, and how modern medicine attempts to reverse that damage. What exactly happened during the crash involving Tiger Woods? The crash occurred when Tiger Woods lost control of a Genesis GV80 while driving at high speed on a curved downhill road. The vehicle left the roadway, struck a median, and entered a rollover sequence. The motion quickly shifted from controlled forward movement into chaotic rotation and impact. How does physics explain the initial loss of control? At high speed, a vehicle carries significant linear momentum. When traction is lost on a curve, that forward motion cannot be maintained along the intended path. Instead, the car begins to yaw and rotate. This transition converts linear momentum into rotational torque, which destabilizes the vehicle and leads to rollover. What happens to the human body during a rollover crash? During a rollover, the body experiences rapid changes in direction and acceleration. G-forces spike in multiple directions, effectively turning the vehicle cabin into a rotating force environment. Even with restraints, the body is subjected to compression, shear, and rotational stress simultaneously. How did the vehicle structure influence the outcome? The Genesis GV80 absorbed much of the crash energy through its crumple zones, helping preserve the central cabin. However, the front section deformed significantly. This deformation pushed components inward, especially in the footwell area, where the driver's legs were positioned. Why were the lower legs the most severely injured? The legs were positioned in a fixed orientation, likely braced against the pedals. When the front of the vehicle collapsed, the energy bypassed external absorption zones and traveled directly into the lower limbs. This created intense compressive and bending forces concentrated in the tibia and fibula. What is the difference between crushing and rotational fractures? Crushing fractures occur when a direct compressive force overwhelms the bone structure, often leading to fragmentation. Rotational fractures occur when twisting forces are applied, causing spiral or angled breaks. In this case, both mechanisms were present due to the combination of intrusion and rollover motion. How does the concept of a kinetic chain apply to this injury? A kinetic chain describes how energy moves through connected parts of a system. In the crash, energy moved from the vehicle frame into the pedals, then into the foot, and upward through the leg. Because the leg was braced, it acted as a rigid column, transmitting force directly into the bones rather than dissipating it. What surgical methods were used to repair the damage? The injuries required stabilization using a metal rod inserted into the tibia, along with screws and pins to hold the fractured bones in alignment. This approach allows the bone to heal while maintaining structural support under load. How does such an injury permanently change movement? Damage to bones, joints, and soft tissue reduces natural mobility. In particular, the ankle and subtalar joint lose flexibility. This alters how forces are distributed when walking or performing athletic movements, leading to inefficiencies in motion. What is meant by energy loss in human movement? Energy loss refers to the reduced efficiency in transferring force through the body. Instead of smooth motion, some energy is dissipated due to stiffness, compensation, or instability. This makes movements less powerful and more physically demanding. How does this affect a professional golf swing? A golf swing depends on a precise sequence of force transfer from the ground through the legs, hips, torso, and arms. When the lower body cannot generate or transmit force effectively, the upper body compensates. This changes timing, reduces power, and increases strain on other parts of the body. What long-term physical effects can result from this type of trauma? Long-term effects include chronic pain, reduced mobility, and increased stress on surrounding joints and the spine. Compensation patterns can lead to additional injuries over time, especially in high-performance athletes. What does this case teach us about vehicle safety? Modern vehicles are highly effective at protecting vital areas of the body by maintaining a survival space. However, they cannot fully prevent injuries to extremities when intrusion occurs. This highlights both the strengths and limitations of automotive safety engineering. What does this case reveal about recovery in elite sports? Recovery is not just about healing bones. It involves retraining the body to function under new mechanical conditions. Even with advanced treatment, returning to peak performance requires adaptation, and some limitations may remain permanent. Finally, the crash involving Tiger Woods shows how physics, engineering, and biology intersect in extreme situations. It demonstrates how rapidly forces can transform motion into injury, and how complex the path to recovery can be. This case continues to inform both medical science and sports performance, offering valuable lessons for the future. If you found this breakdown helpful, make sure to share the video, like it, and subscribe for more deep insights into real-world events explained through science and analysis.